All right, next I'd like to look at the scales of time that are associated with the universe. These are also immense amounts of time that have gone by since the beginning of the universe. And the fact that the universe had a beginning is kind of astonishing, but there's actually very strong evidence to support this idea that the universe started roughly 13.7 billion years ago. And we believe that the universe began with a huge explosion, a rapid expansion of space and time, which we call the Big Bang. And this was from a point of high concentration. So that being the case, let's just assume that that's right. We might ask some questions like, well, what happened before the Big Bang? What started the Big Bang? Well, first we have to try to get a handle on what this really was. We had some point of essentially infinite density, almost, that started to expand rapidly. And it expanded so rapidly that we call this the Big Bang. Now, this is a difficult idea to accept because it's hard for us to understand what could have caused this rapid expansion of space and time at the beginning of the universe. And then what was going on before that? It would be a natural question that we could ask. And we don't know the answers to this. We don't know what caused the Big Bang, and we don't know what happened before the Big Bang. But this doesn't stop us from speculating. One possibility, so we should say here, we don't know. And I'm just speculating, but it's kind of fun to speculate about such unanswerable questions. Here's some possibilities that have been proposed. One is that the Big Bang is basically the end of the last cycle of expansion and contraction. So in other words, universes may expand and contract like this. So we'd have a Big Bang, and then that would expand out to a certain maximum point and then would recollapse. Okay, so that the radius of the universe then, it would start out like this. It would get bigger, 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 like this, and then gravity would take over, it would get smaller, and then out here we'd have the big crunch. This would be the Big Bang. That would be the start of our universe, and we're in an expanding phase now, but what all universes might do is expand to some maximum size, and then this would be the big crunch. And then it might expand back out again. So that would be the Big Bang for the next cycle. Then we'd have a big crunch, and you could have this kind of thing going on ad infinitum. Just has been going on like this forever. And so we could say then that the universe might expand and contract, and so the end of the last contraction cycle became our Big Bang. So in other words, the death of the last universe in this infinite sequence of expansions and contractions then became the beginning for our universe. That's an interesting idea. Then you have to, of course, ask the question, well, what created that previous universe cycle? And then you go, well, the one before that. And then you go, well, what created that one? And you go, well, the one before that. Then the one before that, one before that, one before that. And so you go back into an infinite regression. And I guess that's okay if you just say that it has just always been doing that. You know, it's been doing that forever. You know, so, but that's hard to swallow. But that, in fact, is what is really happening. But it is one idea that's been proposed to explain the Big Bang and to explain what was going on before the Big Bang. Another possibility for what happened before the Big Bang is that there are other universes, and those universes every now and then can collide with each other. And when they collide, they can release energy which might look like a Big Bang. And so the Big Bang then might be the result of energy released from other universes colliding. Now, this isn't necessarily correct, and there's no evidence that there are other universes. But there are some suggestions that they might exist. There are some solutions to Einstein's field equations that, if you interpret them correctly, could lead you to believe that there could at least be other universes. And if there are other universes, they could perhaps run into each other and release energy, and then that energy of that collision could look from our point of view as though it were occurring from a single point, and that's our Big Bang. Now, even if this isn't right, it may give us different predictions that we can test somehow in the future. We don't know how to test for these things yet exactly. We're looking for ways to tell the difference between what we see in the universe today and these different possibilities for what might have happened before the universe began. It's kind of amazing that people are even thinking about things like this, but they are. Another possibility for what happened before the Big Bang, put it over here, is that the universe was created out of nothing. And so we'll call this the free lunch model. And upon first glance, it looks kind of ridiculous. That it actually may have more theoretical foundation to it than the other possibilities that have been mentioned so far. Because when you analyze the vacuum of space, what you find is it's not really empty, but it's filled with different fields and what is called the zero-point energy of the universe. And so it's possible that fluctuations of the vacuum, which isn't really nothing, it's just what we call nothing, but it's really something, it must be because it's got energy in it, could every now and then give rise to a universe like our own. But out of the vacuum, out of essentially nothing. And so, you know, one of the age-old questions is, why is there something rather than nothing? And a possible answer to that would be that nothing is unstable, and it naturally wants to become something. Okay, so that's another possibility. And we'll talk about some of these things in a little more detail much farther along in the class. Number 4, we could say that, and this is kind of in the words of Stephen Hawking, that the question has no meaning. Because there was no before the Big Bang. Time began when the universe began. There was no before the Big Bang. And so what Stephen Hawking meant by this is that trying to find a time that was before the Big Bang might be like trying to find a point that's 10 miles north of the North Pole. Now, there is no such point that's 10 miles north of the North Pole. And similarly, there might be no time coordinate before the creation of the universe. So to put that into more perspective, better perspective, we could ask ourselves the question, well, what is time then? And one way of thinking about it that seems to work is that time is a way of measuring change in space. Okay? Because if there's no change in space, there's no time elapsed. If nothing has changed, then you're frozen in time. So time then is a way of measuring change in space. So if we're talking about the universe before it began, then the universe isn't taking up any space. And so how can there be change in space if the universe isn't taking up any space? So if there's no space, there's no time. And so that's what Stephen Hawking meant by the fact that the question has no meaning. And what happened before the Big Bang, there's a presumption there. The presumption is there was a before. And so you start trying to answer that question. But a lot of times, these unanswerable questions may just be the result of not asking the right question or asking a faulty question. Okay? And then there is another possibility too, and that is that we're not capable of understanding the answer. Assuming there is an answer. Certainly the mental abilities that we've evolved are the result of us having a survival advantage. And so we might ask then, is there really a survival advantage to being able to understand these deepest questions about the origins of the universe and what came before the Big Bang? Maybe it's not necessary for our survival for us to be able to understand things like this. But to me, that's kind of like giving up. Although I consider this to be a viable possibility, I still think it's a lot of fun to try to answer these questions and to do the best we can with our limited minds. Okay, so even though we can't answer a question like this now, we do have a pretty good idea of what happened after the Big Bang. And one of the things that we go back up to the data projector, that we can note is that we believe that most of the significant events in the history of the universe took place in the first second after the Big Bang. And so here, although you don't need to worry about most of these details, you can see that there were a lot of really significant things that took place as the universe started to expand and cool. So here's time 0. Okay, this is time on the horizontal axis, temperature on the vertical axis. And so we go through these epochs that just take the tiniest fraction of 1 second to complete. The universe goes basically we think, a dimension of time manifested from a dimension of space in the earliest part of the universe. And then the different forces of nature start to become evident until finally we get to about 1 second. And then, from then on, all the way up to the present, this is on the logarithmic scale. That's why it doesn't seem like much time has gone by here, is that we're dealing with powers of 10 for our time. So we see that no, nothing much has happened since the first second. All of the things that made the universe what it is happened in this first second after the Big Bang. So during this first second, we believe that the basic properties of the universe solidified. And so examples of this would be the number of dimensions in the universe. So we have 3 spatial dimensions and a time dimension, but we could have had only 2 spatial dimensions, or maybe 12 spatial dimensions and 2 dimensions of time. There are all of these different other possibilities for numbers of dimensions. The speed of light would be another very important factor which determines how the universe works. The mass of a proton, the charge on an electron, and we can go on and on. There's something like 20 of these different factors that we think could have randomly been reset as some other value in another universe, and that they just happen to take on the values that they have here in this universe, which gives rise to life. And an amazing thing about this is if we change these quantities by the smallest amount, the universe is no longer habitable. And I'm not talking about a lot of change. I'm talking about more than 1 or 2%. The force of gravity would be another one. The attraction between positive and negative. So if we change something like, for example, the force of gravity, if we increase it by 2%, it's believed that the universe would have smashed down to become a universe-sized black hole in about 1,000 years. But if you decrease the force of gravity by about 2%, the universe just keeps expanding forever with no stars or galaxies ever forming. And so this is kind of a big question then, is why are the constants of nature so delicately balanced to allow for life to exist? And so this is one of the reasons why people believe that there may be other universes, that each universe that just kind of randomly takes a certain form, and we just happen to be in one of those universes that has all the right constants that are just right, the right number of dimensions and everything else is just perfectly balanced so that life can exist. Now there may be more to it than that. It may be that universes can have babies and they can give rise to children that have similar physical constants if they are able to reproduce themselves better. So there could be something like a Darwin theory of evolution for universes, but we don't know. All we can say is that from our point of view here, if we change these things by just the slightest amount, life, at least as we know it, is impossible. Now, as the universe continues to expand, it cools. And so if we go to a time following the Big Bang of about 230,000 years, the universe is cooled enough so that electrons can start circling around the nuclei of atoms. So atoms start to form. Long before that, in the first second, matter formed out of energy. But this was in the form of subatomic particles. So it's too soon, if we're talking about in the first second after the Big Bang, to say that atoms have formed, because everything's too hot. So we just have this soup of energy which turns into subatomic particles. And this is caused by the fact that E equals mc squared, where E is energy. So this is like the energy of the Big Bang. M is the mass of these subatomic particles, and c, as we saw before, is the speed of light. In this case, it's the speed of light squared. So in this first second after the Big Bang, energy is being turned into mass, okay, by the Einstein's famous equation. In the universe of today, mostly we have matter turning into energy. But in this first second, we had energy turning into mass. But then as the particles started to cool, we could get electrons circling around the nuclei, and atoms started to form something like 250,000 years after the Big Bang. Okay? And then gravity started acting on the atoms. To form stars. So something like maybe 100 million years after the Big Bang, the first stars began to form. And these stars were very big at first, some of them at least, were gigantic. In our own solar system, these stars could extend all the way out to the planet Saturn, and that would be normal in those days. Because mostly we only had hydrogen in these stars, and in successive generations of stars started having heavier elements which generate more heat in the core and make those bigger stars unstable. But in these early times, really big stars could start to crank up, something like 100 million years after the Big Bang. And then, because of the influence of dark matter and black holes which we'll talk more about later, the stars started to collect together to form galaxies. So about 1 billion years after the Big Bang, galaxies formed. And so these are the kind of galaxies that we were looking at in those distance scales. Some were spiral galaxies, and then as some of these spiral galaxies started to collide, we would get elliptical galaxies, which are some of the really big galaxies that we see in the universe. And so this is just, though, still 1 billion years after the Big Bang, and probably not much in the way of life so far. So, as we're looking through it, by the way, I put these PowerPoint slides up on Canvas so that you can review them. But roughly speaking, about 500,000 years, that's when atoms started to form. We think that it might be a little closer to 250,000 years, but somewhere between 250,000 years and 500,000 years. Atoms started to form. Then about 100 million years after the Big Bang, stars started to form, and then 1 billion years it took for the first galaxies to form. But we're still, the universe is something like 13.7 billion years old. And so what happened next? Well, something like 4.6 billion years ago, our solar system formed. And so this means that the universe must have been around for something like 10 billion years before our solar system formed. And this makes our solar system about 1/3 the age of the universe. Okay, so this is a number that I'd like you to remember, is that something like maybe 9 billion years after the Big Bang, or 4.6 billion years ago, our solar system formed. Which means that our solar system is just 1/3 the age of the universe. So we have to try to understand this, why this is true. Why is it that life couldn't have formed at some earlier time? Or is this just, it just happened to form at this point, and there was a lot of life earlier on? Well, it turns out we don't think there was much life earlier on when galaxies were first forming. And the reason for this is that the universe was primarily made out of hydrogen and helium in these early times. Which I'll abbreviate by H and HE when I talk about these in subsequent lectures. So this is not a good mix of elements for life. So we need to be able to form heavier elements. So the question is, where do we get these heavier elements? If we just had hydrogen and helium mostly following the Big Bang. And today, life is made out of carbon-containing molecules, certainly. Now, hydrogen may be a part of some of the molecular combinations in life today, but you definitely can't have a life form that's just made of hydrogen and helium. So the thinking is that when big stars get old, they explode. And we'll talk more about how this happens later. But by big stars here, I mean ones that are even bigger than our own sun. You know, way bigger than our own sun. Maybe 30 times the mass of our sun. But eventually, these stars end up blowing up. And this term for the explosion of a large star is called a supernova. And so the thing with these supernova explosions is that we think that this is the origin of the heavier elements. So in other words, during a supernova explosion, heavy elements are synthesized and then blown out into the intergalactic medium. Well, all of the elements on the periodic table, which we can see over here on the left-hand board, hydrogen and helium are just the top two elements. But we have lithium, beryllium, boron, carbon, nitrogen, oxygen. Then you go down to some of the bigger elements. You've got uranium. So these are all really important for life. And so during the supernova explosion, heavy elements like carbon, nitrogen, oxygen, and even heavier elements like uranium are formed and blown out into the galactic space around it. And so these elements then, that are blasted away, can then cause a cloud of gas and dust to become infused with these heavy elements and can then form a new generation of stars. So this is what causes the formation of new stars and planets. But the trick is, it takes time for enough of these supernova explosions to happen so that we get enough of these heavy elements in the galactic medium so that the new generations of stars can have the raw materials for life. So that's the key then to understanding why it took so long for our solar system to form. So we could ask then, well, why is the universe so big and so old? Is that a question we can really answer? You'd think, well, it's just the way it worked out. You know, you'd say something like that maybe. But we can actually answer this question. because it takes time to make these heavy elements. And so because of this, we don't expect that there was much life a billion years after the Big Bang. Maybe some life. You know, I mean, there could be a situation where a supernova could explode and produce enough of these heavy elements so that you would get a civilization that could form, or even some simple forms of life that could form a billion years after the Big Bang. But I think the odds are low of this happening. And so as time goes on, maybe you have to wait 6, 7, 9 billion years before you get enough of these elements so that a solar system like ours can form. And so we can say that in general it probably takes many billions of years to build up the sufficient concentrations of heavy elements for life. Okay, and so the fact that we're viewing what's happening and asking these questions is an indication of the fact that we're here. Because if we weren't here, we wouldn't be asking these questions. But the reason that the universe is so big and old is that it took time for these elements to build up so that we could be here to ask these questions about the universe. And that there probably weren't a lot of creatures that were around asking these questions the first billion or 2 or 3 or even 4 billion years after the Big Bang. And so that's why the universe is so old. The universe is so big because it's expanding rapidly. And so if it's expanding for billions of years, it has to get big in the process of doing that. And so it's old because there's a delay time in how much time it takes to make the heavy elements. And it's big because it was expanding rapidly close to the speed of light for many billions of years. And so therefore, the universe has become